Greetings. Today we are going to cover the second part of our slides, the one that is labeled 425B. And so we are looking at concentration cells. Concentration cells exploit the effect of concentration changes in cell potential. So when you look about concentration, there's something about variation in concentration of these cells. The cells, they have the same half reaction in both cell compartments. So if you have the two compartments, then we have same solution, okay, in both cases, but the only thing that differs are the concentrations. So we have different concentration of the electrolyte. As long as the concentrations of the solutions are different, the cell potential is greater than 0 and the cell can do work. Okay, so I hope we understand what a concentration cell is. An example of a concentration cell that we are having here is the copper ion half reaction. So we have two cells that we have that have been shown here. So in this case we have electrolytes, same electrolyte but different concentrations. And so their half equations will be the same. The only thing that will differ is that. So we have an overall reaction of that. And the E0 cell is greater than 0 as long as there's a variation in the concentration. But in this case where the concentrations are the same, we don't expect anything to happen, and that's why you are seeing it at 0.00 V, because no work will be done. There's no potential difference between the two because of similar concentration. So the cell is no longer able to do work once the concentrations are equal. So we have an example here of a concentration cell consisting of two. We have silver ion half cells. In half cell A, we have the electrolyte is 0.001 silver nitrate. In B, we have it as 4.0 times 10 power negative 4 molar. And so you're asked that what is the cell potential at 298.15 Kelvin. If you look at your notes and you see the breakdown of how you approach that question, that the cell standard half cell potentials are identical. So the E0 cell is 0, and we find E cell from the Nast equation. So the E0 cell is 0 already, but for the E cell we need to determine it from the Nast equation. So the half cell A has a higher concentration, this one. So the silver ions are reduced and played out on the electrode A, which is therefore the cathode. So we have the cathode there. In half cell B, silver atoms of the electrode are oxidized and silver ions enter the solution. So electrode B is thus the anode. As for all voltaic cells, the cathode is positive and the anode is negative. So with that, then we can be able to break it down, write it, draw it. If you're asked to draw the cell, you should be able to draw it. So the silver ion increases in half cell A and increases in half cell B. So the spontaneous reaction, it decreases in A, decreases there and increases in B. So the two concentrations are there. You need to write the Q or KEQ of this reaction, and that is what you'll have here. So E cell will be E0 cell minus 0.0592 over 1 V log of the two concentrations, and it gives us that value. Please try do the calculation just to confirm that what is here is the right thing. How do we measure pH in the laboratory? So when you look at our pH meters, which I hope we have been exposed to now that you're 4th years, I want to believe at least each of you has touched a pH before you walk out of the university. Otherwise it will be criminal. So if you haven't, please try and just find out how the pH works and how it's basically operated. So the operation of a pH meter illustrates an important application of concentration cells. The glass electrode monitors the concentration of hydrogen ions of the solution relative to its own fixed internal hydrogen ion. So within the pH meter, we have a fixed concentration of hydrogen ions within its electrode, but you also have what is in the solution here. Okay, so we have glass electrode, we have reference electrode, and then we can be able to determine the pH. So this is an old style, a different type, and this is a modern type of a pH meter. So this uses a combination electrode. This one includes two electrodes, two separate ones. Okay. So in the lab, we use this to test a number of things, from the pH of even the water or any food substance. The beauty products that you use on your skin, their pHs are very, very crucial for us to understand. Okay. So we have different kind of ions that can be detected by specific electrodes. So these are the ions, the anions, some are cations, and then where they are basically found in. So you can find CO2 in blood. You can be able to measure CO2 in blood or water. The hydrogen carbonate can be measured in the amount of it in water. Fluorides can be determined in all these samples. And we can have hydrogen ion laboratory solutions, soil, natural waters, because this will give us the pH. So these are some of the ions that are measured with ion-specific electrodes. When you talk of mini-microanalysis, the word that first came into mind was mimicry, biomimicry. But this is mini-microanalysis. So a microelectrode records electrical impulses of a single neuron in a monkey's visual cortex. So this is a basic picture of that. The electrical potential of a nerve cell, because we're looking at a single neuron of this monkey's cortex. So this potential is due to the different concentration of sodium ion and potassium ions inside and outside the cell. And so that is what creates the electrical impulses within the neuron. And so we see some basic application there of electrochemistry. Then the other part that we also want to look at today is electrochemical processes in batteries. A battery consists of self-contained voltaic cells arranged in series. So the individual voltages are added. So when we look at a battery, you can always make a reference to that. It consists of voltaic cells. So it is made up of voltaic cells and they're arranged in series. Okay, they are arranged in series. So then you sum up their individual voltages. A primary battery cannot be recharged. The battery is dead when the cell reaction has reached its equilibrium. So once the reaction has reached its equilibrium, the battery basically dies. But a second battery is rechargeable. I hope we have seen rechargeable batteries. Once it has run down, electrical energy is supplied to reverse the cell reaction and form more reactants. So you can be able to reverse the process and be able to start all over again. So that is for a secondary battery. So these are the other types of batteries that I would want you to read through, please, and just look at the reaction that happens at both the anode and the cathode. And then once you look at that, then you get the overall reaction that you find in an alkaline battery. And let us understand how these batteries work. Then we have the other type of battery that you use in your watches, the silver button battery. this is still some aspects of industrial application of electrochemistry. So you see the components there, and we look at the half reactions and then the combined cell reaction. And once you combine that, then you get the E cell, which is 1.67. Okay, so this is another type of battery. Then we have the lithium battery, widely used in watches, implanted medical devices like the heart pacemaker here, and remote control devices. Once again, that is what we have in the anode, that is what you have in the cathode, and then you combine the two equations to give you this as our overall reaction. So these are some of the components, some of the different types of batteries and their components that we need to be able to appreciate. Lead acid batteries is secondary battery and it is rechargeable. So we need to be able to know, when you have a car and you look at the battery, at least you understand how this thing works and the application of electrochemistry. So these are the reactions in a lead acid battery. And it is important that you understand what happens in the anode, in the cathode, and then the overall reaction. Okay, so this is as it loses discharge, and this is when it is recharged, so that you can be able to use it again. Nickel metal hydride battery, same things. We basically look at what happens in the anode, what happens in the cathode, and the overall reaction. And the one that we use in the laptops is lithium ion batteries. They are lasting. When you buy a laptop, it shows you how long it takes that it can be able to sustain charge. So they vary from laptop to laptop. But this is basically the battery, and this are what happens within those batteries. It is used to power laptop computers, cell phones, and camera recorders. And the final one is the fuel cells. In a fuel cell, also called a flow cell, reactants enter the cell and the products leave. So we have the reactants getting into the cell, the products leave. As this happens, there's electricity that is generated through combustion. Okay, so reaction rates are lower in fuel cells than in other batteries, so an electrocatalyst must be used to be able to lower the activation energy. So that energy there, the barrier that we have, is lowered by this electrocatalyst. So this is an example of a fuel cell. We have the hydrogen there that flows in, oxygen flows in, and then water comes out. Our electrolyte is there. Okay, and then we have our electrodes also indicated there. So this hydrogen fuel cell, we can also be able to discuss it in terms of its anode reaction, cathode reaction, and overall cell reaction. So I want you to look at that and just try to follow them and read about them to enable us understand the various types of cells that we have in electrochemistry. Otherwise, thank you.